for the three-dimensional hydrogeologic conceptual model for the Indian Wells Valley groundwater basin. And the report's developed by Paul Thorne, Max Halkier of Ramboll, and they're in Denmark. That is where they're located. They're supposed to be getting on the phone to help answer any questions. And then myself, I'm Tim Parker, and I'm a technical consultant, independent technical consultant, and I'm a contractor or contracted consultant to the Indian Wells Valley Water District. And I'll be giving the presentation. It's about 70 slides, so I'm figuring about an hour, might be a little longer. I'll try to break a few times during that for questions at key kind of breaks in the presentation. And just wanted to say that this is really funded by, this is a study that's funded by the Indian Wells Valley Water District, Mojave Pistachios, COSO Operating Company, and the symbol over on the right is Searles Valley Minerals. Meadowbrook Dairy also has contributed to this project. And the project really is focused on developing more information on brackish groundwater in the basin as a potential alternative supply. It would not be a long-term supply, but more of a short-term, when I say short-term, 20 or 30 years, something like that. Everybody hopefully knows a little bit about SGMA, the Sustainable Groundwater Management Act, and this is a critically overdrafted basin that has to be in compliance. In other words, having a sustainable groundwater supply, meaning groundwater levels aren't continuing to decline, in about a little over 20 years. So there's a lot of different things going on with that. This is really not about that SGMA project. This brackish water project's a separate project, and it's being separately funded. So with that, and I've already kind of gone over this, but this is really, now I say the largest aggregation of digital geologic and water quality data that's been assembled. There's been a lot of work done in this basin over the decades, and part of that is the Navy is here, and the Navy has developed, co-developed, I guess you could say, with COSO Operating Company, and the Navy's here, and correct me if I say anything wrong, please, because I want to make sure I'm accurate. But basically, they've developed a geothermal supply here, and that's so there was a lot of deep geologic investigation initially. They focused, some of the work was focused more shallow in the later years, but that's really why the basin has a lot of good information that's been developed as background. What's different about this is that we are putting all the data, tabular, spatial data, into electronic digital format, and the district is maintaining it. And so previous efforts have been done, but they're not readily available and won't be haven't been stored effectively. So this is what's different about this, and it's different in terms of the SGMA project where they're developing, and I want to make sure everybody understands this, a hydrogeologic conceptual model that's more narrative and sort of a picture, not a digital one. So this will be useful in the future to help understand the strengths and weaknesses of the current groundwater flow model and improve that over time. And with this digital model, you can actually export layers out of the hydrogeologic conceptual model, the 3D one, and make ModFlow layers out of it. So just wanted to explain that. So it's not meant to replace or compete against the SGMA work. And so really I want to just explain what is a HCM. I'm going to use that acronym because it's easier than saying the big words. But basically, it's really a framework of a geology. Now, why is that important? It's because the geology controls groundwater flow. That, and of course, pumping controls it. But geology determines where the water has space and where the best flow paths are. And gravity controls how water flows, and the water is going to go where the least resistance is. So those are just some general concepts, why it's so important to understand the hydrogeology as well as possible. And I'm a geologist, I'm a hydrogeologist and engineering geologist, so it's I'm a little biased, I guess you could say. But it's really important to understand that. And so it's critically to understanding the relationship between groundwater and the geology. And so that's what this hydrogeologic conceptual model is really meant to do. And how do we do the HCM? I'm going to kind of move around a little bit here, but because I don't have a green laser, and as you may know, red and blue do not work on glass. But so really, one of the things that happened when we started looking at brackish water, Stanford came in. I knew somebody at Stanford, and they came in and did a pilot test using a couple of different technologies. One of those was electromagnetics, time domain electromagnetics. And one of the recommendations out of that report was, gee, you ought to consider aerial electromagnetics, that is, flying electromagnetics. You can collect a lot more data a lot more quickly, cover a lot of area. And that led actually to us being involved with this Stanford Groundwater Architecture project, the GAP. And so there's a workflow developed for that, and that's kind of what we're following for this project. And the GAP project is a three-basin pilot. So there are 2 other basins that are taking on this similar kind of an effort where they're doing SkyTem data, comprehensive data acquisition, bringing it all into basically a data management system. It's called GeoGIS. I'll explain a little bit more about that. And doing so this additional geophysical data. SkyTem is the name of basically the company that does the time domain electromagnetics. It's Danish. There's a few other companies out there that do this, but the Danish group kind of, I think, invented it. And they are the ones that are a partner. It's Rambo is a partner to this project, along with the State of California Department of Water Resources, the State Water Resources Control Board, and the Kingdom of Denmark are all putting money into this. 1/3 for Denmark, about 1/3 for the state, and 1/3 for the 3 different basins that are involved. So this is being created in software called Geoscene 3D. You can search that online and find it and see the details of how it works. So it's basically development of a conceptual model skeleton. I'm going to go over the geologic history based on a lot of the reports, good reports and studies that have been done here. So that's very important in developing the skeleton. And so it's reviewing previous studies and then developing a 3D layer model. And then through this process, of course, reaching out to folks like you. We've been reaching out to various groups, and then going through a draft and a final 3D HCM, and then input it to a groundwater flow model would be a typical process. This is data. We don't have a project for that. It's just we're going to complete this. What this is, by the way, it's the traditional HCM. There's one step beyond this where they will use geostatistics to fully populate the model in terms of the cells within the model. And that will be in terms of the texture of the geology, sand, silt, clay, etc. And then if the geophysics looks good enough, we may be able to populate it with the hydraulic conductivity distribution as well. They've done that over in Denmark, but we'll see how that goes. So I'm going to go through these relatively quickly, this next couple sets of slides, because it's really just explaining the software, giving a little background on it. So GeoGIS is a data management system. It's comprehensive. It's open database data management system. SQL Server, MS Access, spreadsheets. You can use different types of storage methods for the tabular data. It's developed over more than 25 years by this company called Ramble, and it's focused on water resources management. Denmark had their basically Sigma back in the 90s, so that's kind of what prompted some of this kind of work, the AEM, the development of the SkyTem, and these kind of bringing everything into digital formats. And the users over there are water agencies, county waterworks, etc. And so it's, as I said, open database format system. They say it's free of charge. There's some licensing that you do have to do. So again, over there, they've got the different types of, they've broken it up into different types of things, all borehole information, grids, time series, geophysical logs, SCADA data, external databases, local SQL server or access, also on the cloud. Things are stored in the cloud, so that's possible as well. A similar set of data set. So you can have multiple ways to set it up, is I guess the point. And then just this just shows an example of some of the interfaces. You can do queries. Here's all the tables for the different types of borehole data. You can have water level data, water quality data, all kinds of different data sets. Some of its capabilities, water level trends, does some simple mapping, and then you can also export things in tables or connect your tables to something like ArcMap, so you can do it in GIS. And this just shows what the database looks like. You've got database queries, import and export capabilities. You can do shortcuts, different types of forms, design different forms for templates, for reporting information, etc. And then, so here's an example of a log that was output. So it has your geophysical log, well construction information, and then lithology. So it's all automated. You just design the template and how you want it to be output, and then it will print it out. And this again is just an example of a groundwater level trend plot that comes out of this system. The Geoscene 3D is again a hydrogeologic conceptual model builder, and it enables visualization of a broad range of geoscience data, well logs, geophysical data, soil water chemistry, terrain, surfaces, geological layers, and you can do manual or semi-automated production of basically generating surfaces off of points. So for those of you into that kind of thing, so you can generate a surface, you can put in control points, and it's basically geostatistics you're generating this with, and then export those layers for processing in other software like models or ArcGIS. And here's just a list of the different data types that this stores. And one thing I've heard from both of these companies, they can take any data. And I have yet to find something they haven't been able to take. But anyway, so this just shows an example. Seismic data, the segue files, for example. And again, just a little bit more on the different types of data and how they're stored, the 2D versus 2D surfaces, 3D grids, 2D points, and so on. So it's a very complicated software to use, actually. I don't know how many people use GIS, but there's a ton of different drop-down menus, and then there's a ton of menus in those menus, so it's not something you just pick up and do. It's a complicated software, but it's very powerful for visualization and understanding. And so now I'm going to, I don't know if there's any questions on the software. Okay, so now I'm going to go into the actual HCM report, the Hydrogeologic Conceptual Model report. And so there's an introduction in the report. I'm not going to go through the report verbatim. Basically, I'm going to talk through a number of figures. But there's a regional geologic and structural setting. This is the historical geology, I should say. An inventory of available data, the HCM development, the process for the development, We'll talk about the basin geometry, the principal hydrogeologic zones that were developed, uncertainty and data gaps, references, and then the appendices. So, we are about here at the southeastern corner of the Sierra Nevada, and you may ask, why did I put up this map? Well, it shows kind of the regional tectonic setting. And this is a very interesting area. This is the Walker Lane block, and then the Eastern California shear zone, belt, I'm sorry. This is the shear zone down here, and then this is the Central Nevada seismic belt, and I forget what the I stands for, but basically what you see here is a result of tectonic development of North America, and about a little over 250 million years ago, this continent used to have a convergent boundary. So there was a crashing of the two plates, the Pacific plate and the North American plate. And what that resulted in was a island arc complex. And here's just a picture of that. So you had this one plate crashing under the other, and you can see everybody know where the coast ranges are. Here's the coast ranges. Here's the Sierra Nevada, and here's the Great Valley. And so when this crashed, it actually created the Sierra Nevada and the Central Valley of California. And that's sort of a rigid plate when you look at it. And then as time went on, a migration of a junction occurred from the south, and that created the San Andreas fault zone. And so this is what we have today, and you can see it's what we call a right lateral strike slip zone. And the same thing is occurring out here. And what we actually see is happening is part of this is there's an extension of the, or spreading and thinning of the crust here all across this area called the Basin and Range. And if you look at it here, what happens is you get these normal faults. Basically, the crust is spreading apart, and these blocks are dropping down out in the Basin and Range. And that's a similar thing that's what happened here. You had the Sierra Nevada formed a normal fault along its front a number of years ago. And that was what prevailed until about 2.5 million years ago, and then it became more of a strike-slip fault. And that's important to understand as I go into the conceptual models. And I'll explain that as we go. So here is the basin as we see it now. And so what we've done is we've subdivided it into two areas. The El Paso area, we did call this the main Indian Wells Valley area previously, but we think it's probably more appropriate to give a geographic name, the China Lake area. So this shows the basin in its current setting. And you'll see there's the Fremont Valley Basin to the south, the Rose Valley Basin, the Coso Valley Basin, Salt Wells, all adjoin this basin. And some of those boundaries allow some level of flow. Not a lot, but it's been, this is the way the Department of Water Resources is Bulletin 118. This is who actually mapped this basin. That was back in like the 70s. And so now back to the geology. So when the Sierra Nevada formed, there was prior history of geologic information there. Prior to the Sierra Nevada forming, North America had basically was a plain where there were ocean deposits. And those remain as remnants, these Paleozoic deposits that are these funny colors in the El Paso Mountains and the Sierra Nevada. And you see sitting on the surface, the Quaternary, the more recent sediments. And basically, what's underlying those are a series of terrestrial materials that were deposited as the basin formed, the Indian Wells Valley Basin formed. And there's been a lot of work done that by a guy by the name of Monastero with the Navy. And here's a table that we took from some of the work that he did. I know you can't read that. One of the things I wanted to point out was, and I'll show this, is that it shows the timing of these different deposits. So here we have the Mesozoic 250 million years ago where the Sierra Nevada formed. And then that was with the onset of normal faulting, and that resulted in a lot of sediments being deposited in the basin. You had the Goler and Ricardo group formation that were deposited on top of the Paleozoic sediments, and those were largely terrestrial, so rivers, lakes, and some volcanics flowed into this area. Then during basically the Miocene to Pliocene, this normal faulting accelerated and caused basically a lot of sediments to flow into the basin, filling the basin. And this was a lot of work that was done by the Navy and Monastero, where they came up with this concept of the White Hill sequence. There's a anticline up in the northeast corner of the basin where it was first mapped by Kunkel and Chase. And what Monastero supposed was that this whole sequence largely filled the basin. And it was a combination of an ancestral sort of Owens River with river deposits coming into the basin, along with a lot of debris coming off of the Sierra Nevada. And actually, this is a hydrogeologic conceptual model from his work. So this is 7 to 3.5 million years ago. So you had this normal faulting occurring along the Sierra Nevada, and a lot of these very coarse-grained mud flows, they call them breccias, and debris flows coming off the Sierra Nevada. You've got alluvial fans as well, which you have currently today coming off of these large drainages where you see these slopes coming off of the mountains. You've got basically lake deposits, fluvial deposits, and some sort of delta deposits, and then basically some Aeolian sands perhaps, but you've got alluvium coming off of both of the Argus Range and the Sierra Nevada. And if you look at this, you can see sort of this concept where you've got this inner fingering of these deposits coming off of the Argus to the west and Sierra Nevada to the east. Now that goes up to the Pliocene, which is about 3.5 to 2.5 million years ago, depending on who you talk to. Then we got into the Pleistocene. And this is where you had a lot of glaciers, periodically glaciers forming and then melting. And this actually is some nice work that was done. And if you look at the topography, you're basically going downhill when you go this way. And so there was a whole string of pluvial lakes, they called them, that were strung together. And the Owens River contributed a lot of water, and there were very high stands of that river. It also contributed a lot of sediment. These glacial melts would have huge fluxes of sediments. In fact, if you go out and you drive along the highway and up Brown Road, you'll find some huge boulders that had to have been deposited by immense flows. And if you look at different parts of the country, you can find areas where you had some sort of an ice dam, perhaps, and then just a huge flushing of water came through. So we know that there was a lot of that kind of activity going on. And then here's a diagram that's out of the report that shows the extent, some of the high extents of the lakes that were a result of this glacial pluvial system. And why is that important, you might ask? Well, because it kind of tells us where to look for the lakes, and actually it's based on where the lakes were, but so it's circular, but basically this shows the extent of some of the basically lake bed deposits, which were clay and sometimes sandy. Now here's a diagram that is out of another report that shows kind of a concept. It's another hydrogeologic conceptual model, and this would be during the Pleistocene, where you saw this Owens River coming out, and as it hit and came through the Rose Valley entrance, it dumped a bunch of sand and formed a delta, and then there's lake deposits around it. That's one concept, but it helps to visualize what the subsurface looks like. You can understand this, understand a concept like that. And so we know that there's lake bed deposits. By the way, there is something called a sag pond that's also been postulated. We don't, in our geophysics, and I'm going to go through this, we don't see as much evidence of that. We see evidence where there are some clays, but they don't seem to be as extensive as what would be suggested in that concept. And then here's another conceptual model that's been proposed, and this is more, I would say, modern, where, here's the Sierra Nevada, you've got these, what we call quaternary, which means recent, basically, from now back through the Pleistocene, so it's about 2.5 million years. And so you've got these alluvials, basically water and air deposited sand, silts, and clays coming off the mountains, and that's what you see in the basin. You've got these striking faults that are basically vertical. Most of these faults are vertical that are the right striking. And then you've got a delta deposits with some lakes and lake bed deposits. So again, that just why is that important? It's important to understand the geology and how we map it in the hydrogeologic conceptual model. So I thought I'd stop now and take any questions or comments. If not, I'm fine. Yes. Yeah. Uh-huh. This is historical. This showed what the pluvial lakes basically looked like, the Pleistocene period. And during the Pleistocene, we have lots of data that's been collected that indicates, based on the soils, the age, the quality, and the geography, that this was a source off the Sierra Nevada of water that went all the way down to Panamint Lake and over to Manly as well. So, there was a huge source of water coming off of the Sierra Nevada when the ice melted. And there were a number of periods this went through. So it's not now. Yes? Well, yeah, we know there's some water coming from Rose Valley. We don't have a good handle on how much, but it's been estimated in the model. So that's one of the areas that we see we could get some more data on. Also, the water quality changes there. Sure. Keep going. Okay. So this summarizes the data available that's in the hydrogeologic conceptual model. About 1,000 wells with lithology, and so that was probably our biggest struggle. Was a lot of these are well completion reports coming from drillers that are handwritten and had to be digitized. Students did that at Sac State, and we have done a lot of QA/QC on that. Then there's 61 digital or geophysical logs, which were paper that had to be digitized using a fancy oil and gas software. Groundwater level monitoring measurements are largely by Kern County Water Agency. They store the data, and Navy collects data as well. 111 wells at 338 screens, 2006 dissolved solid samples, TDS, from 563 wells, and the most recent data used in 391 wells. 11 seismic lines covering about 150 miles. Those were done by the Navy Geothermal Group. And 5 Stanford pilot test locations using surface time domain electromagnetics and downhole magnetic resonance, and then 500 linear miles of SkyTem data, which I'll talk a little bit about that. So this, I'm just going to show some figures now, the distribution of the wells. And if you can see the pink dots, they're wells that are up to 350 feet deep. The yellow ones are 350 to 1,000, and the blue ones are over 1,000. And you can see most of them are pink, so there are a lot of shallow wells, not a lot of deep wells, and we've got, you can see the spatial distribution in the El Paso area is pretty low. There are more wells than what we're showing here, but these are the wells that are in our system. And the same goes for the Navy base. Then over here, this shows the geophysical logs that have been digitized, and you can see the distribution of those then. I guess I better stop walking back and forth. And so on the left, we have the Kern County Water Agency groundwater monitoring well distribution. And then over on the right shows the distribution of the TDS wells that have TDS measurements that are in our system. This shows the seismic lines on the left. And then over on the right, it shows those triangles the green triangles show the Stanford pilot test. And then this shows the SkyTem work, the lines that were flown. We weren't able to cover the whole basin. The Navy has restrictions on what they're doing out there, so we could not cover the whole area. Also, you'll note there's a big hole where Ridgecrest is, where the SkyTem cannot fly over buildings. Electromagnetics doesn't like pipes and electrical fields, so that's where you see gaps as well, where we had electrical lines and that kind of thing we were flying over. But that's basically the coverage you see. You'll note that the density of lines is a lot higher in this area. When we were in the process of planning the SkyTem data, we worked with the modelers, DRI, Desert Research Institute, and they said they were having trouble converging and calibrating the model in this area. And it's because there's appears to be a couple of faults there that disrupt flow. And you could see that in the groundwater level contours, but it wasn't well documented in terms of mapping. And this diagram on the right just shows what the system looks like. So here's a helicopter. It flies this big hoop about 150 feet off the ground at 50 miles an hour. It's got a generator and a computer system. The pilot just focuses on the flight path. The computer is not connected to the helicopter. This has GPS and magnetics, a video camera, which we didn't turn on the base. We turned it off, and then it has a receiver, sending and receiver to send pulses of electromagnetic field into the subsurface, and to receive it and to generate a electromagnetic profile. So Paul and Max, are you on the phone?
Yes, can you hear me?
Yeah, okay. Hi, Paul. We're just getting into this part of the survey. Have you been on long?
Yeah, maybe about 20 minutes, 15 minutes.
Okay, perfect, thanks.
And we've been following the live stream as well.
Right, so we've already covered this in terms of SkyTem and the reason and the kind of the process for doing this. And here I'm going to get into now some of the explanation of the colors you're going to see in some of the diagrams. So these logs came in written descriptions, so it's better for visual in a 3D framework to have colors you can identify with. So you can see the dark gray is fill, the yellow is sand, light red is gravel, or it actually looks like a pink to me, but orange is sand as well. Brown is clay or silt, dark brown is clay, and then we've got some volcanic descriptors as well. Tan for tuff, black for basalt, light gray for granite, conglomerates purple, dark red for sandstone, blue could be granite or basalt, and then limestone's green and unknown's white. Don't expect you to remember those. I'll continue to repeat them, but this just is to show you the process that we went through to put these into the visual context. And this shows a diagram of SkyTem output. I'm going to spend a few minutes on this because, again, it's color related, and it doesn't always match what I just said, but in terms of the different lithologies. But basically, we have clay is green to light blue. When you get over to dark blue, it really is a saline clay typically. So that's important to know as we're talking. This area here is sand and gravel, the yellows and oranges, and then when you get into more of the reds, it tends to be more unsaturated sediments, and over here we're into bedrock. So again, bedrock, unsaturated sands and gravels, which are probably saturated, then clay, then saline clay. Pretty simple, huh? Okay, because I'm going to show a lot of diagrams with these on it. And then, so here is a section that goes from the west to the east across the basin. Some of you may recognize this. This is Bureau of Reclamation Well 2, and it shows what that well logged. And so this is all clay. Here's some sand at the top and some clayey sand. And then here you can see the diagram. So this is unsaturated up here. And then we have sand, sort of this yellowish, grading into a clay. So it's a coarsening upward sequence. And then you've got a sandy clay in here where it's kind of bluish to yellowish. And then a clayey sand down here. So it looks like it matches up to some degree with this log. One thing I'd point out about some of the logs, some are higher quality than others. There was somebody logging this, but they're logging cuttings, and there's some drawbacks with that, especially when you're dealing with things like clays and sands mixed together. They tend to come mixed up, and then there was an E-log that was done as well. So Quality is everything. Some of the holes were cored continuously out here, and those you can see basically when you look at the detail in the log, and you'll see what I mean. There's a lot more colors, a lot thinner distribution. This shows another cross section, and here we've got some water quality samples as well. And so these reds, I believe, are 5,000, greater than 5,000. This is yellow. It's 2,000, and the green, or 1,000. I think the green is 500 to 1,000, but I'll show another diagram with that. But what's really important to point here is that you need all different types of data to make this all work. So when you're looking at the geophysics, it's good to have lithologic data you collected at that point, in some of the points, as well as water quality. So you can differentiate between a clay versus a sand and a saline clay. So if you know the salinity, then it helps you better understand what you're seeing in the geophysics. And here's another example of, this time we're showing a gamma log. And here is BR10, and here you can see it's got sand, clay, pretty thick clay, and a sand. And then over here, and you note the detail, and here you can see this gamma is really, it depends on the type of clay, but it's really indicative of the amount of clay in a given area. And you can note that there's a lot more. This gamma log's telling us that this clay isn't just a single clay. It's not all the same going down. It suggests that it's got a lot more clay in this particular area, and maybe there was sand mixed in with it. Here is one way to look at it. Now here's what I mentioned earlier about the continuous cores. Here you can see, I don't know if you can see where you are, but I can certainly see it. So there's a lot of different colors in here because somebody detailed and looked at every sample, and they were able to, when you core continuously, you basically put a core barrel down on a wire line, you pull it back up, you open it up, and you look at what's in it, and you describe it. Now, you don't get 100% recovery. You know, it depends on the material. When you're not getting recovery, chances are you're not in a clay. You're probably in some kind of loose sand and gravel material. So that gives you an indicator. But basically, you can see here that there's a lot more description. There's a lot more heterogeneity in the materials, and that's what we would expect in this kind of an environment, actually, because everything's interfingering. And the gamma log kind of speaks to that as well, where you can see there's a lot of picks, a lot of kicks in clay through here, and you can kind of see that in the colors that are described. And this is, so I mentioned that there were 11 seismic lines. We didn't get the segue files. Those are actually the digital files. We got images, but we registered the images and put it into the 3D conceptual model. So, and we were able to make some pics, and there were also some interpretation provided by the Navy, but not all the interpretation. We're still looking to hopefully get some more information on that at some point, but who knows. Anyway, so this shows the interpretation based on the seismic stuff, and so basement down here, you see it's about, this is meters. So this is about 1,500 meters, or about 5,000 feet. Well, a little less, okay? But so you can see clay materials, sand, and some sandy materials down here. So we're trying to use all the data in as best a way as we can. Now this shows a map of the basement. So I'm going to start building blocks on the hydrogeologic conceptual model, the layers we've developed. And the first thing is to define the basin. With the seismic, with the geophysics, the AEM, we were able to see the basement to some degree around the edges. So we could tag the basement around the edges. With the rest of the data, there aren't that many holes that go down to the basement. The snort holes do. And supersonic, what's that stand for? Naval Ordnance Research Track. I knew somebody would know. Okay, thank you. Naval Ordnance Supersonic? Naval Ordnance Research Track. So those two holes basically went down to Baker. There are a few other holes that tag basement, but so we're kind of we've got a pretty good handle on it, but it's not for sure. But this shows a map, and basically the dark brown is below 4,000 feet, and 4,000 to 2,000 is the lighter brown. So you can see it's basically the basin's deepest in this area, and its shallows going up. And this is as expected when you think about the way the basin formed with this. It's basically a half graben with this normal fault on the west side from the Sierra Nevada dropping down as sediments are flowing in. So that makes sense. And then this is shallower over here, it appears to be. And you'll see in some of our diagrams there appears to be a couple of faults running through here, where there's faults running all through this. These black lines are faults that have been mapped. Most of these are relatively vertical lines, and they're typically right lateral slip faults, which means if you were standing on looking at the fault, that things move to the right, if that helps. And so anyway, so here I think we're going to see some sections now. Right, so these are the three sections that are on the next diagram, those three red lines that show basically the outline of the geometry of the basin. And so here's running west to east. There's a little indicator up there. I'm not sure you can see it, but it's going right across the middle of the middle of the China Lake area, and you can see it's down to, let's see, 2,000 meters elevation is about where the basin is. Here's the Sierra Nevada frontal fault. Then moving down here, we're looking across this neck from this area right here. And you can see again this Sierra Nevada frontal fault, and you can see it isn't quite as deep. And then looking across from the southwest to the northeast, this is pretty interesting here. You can see that we've mapped this El Paso area as being a much shallower basin in terms of where the basement is. This is all filled with sediment, obviously. But then here's the Sierra Nevada frontal fault cutting across here, and it looks like there's two segments of it running through here, and it's much deeper there. Yes? Good question. It's typically the granitic rock. There may be, we haven't mapped it very well. The granitic rock is what we're considering. There may be some Paleozoic sediments sitting on top of that. They may have been metamorphosed. Then on top of that is the Golar Formation, and then the Ricardo Group. Those are a little bit older sediments. Then you have this White Hills sequence sitting on top of that over in the China Lake area. And then on top of that, Pleistocene sediments, and then finally the recent sediments. Yes?
Have you looked at any of the information that was given to the Ormark Court and Mike Stoner at the Navy, all the cutting samples that were done on North Brown Road and the E-log? Hasn't that been entered?
Well, we got what E-logs we did. I don't know that they were in particular those E-logs. We haven't gotten any cutting samples.
Cutting samples?
No, never. We've never. Yeah, I don't know. Okay.
Well, they're all marked, and there's like 15 of them. They're long boxes.
They're in core boxes.
Yeah, 4 boxes.
They're about this long, that wide. You can only put so much dirt in a box and be able to pick it up, let me tell you.
They're all essentially done styrofoam cups.
Oh, okay, yeah, Don, did you have a question or comment?
I was going to make a comment. Snort 1 is bottom in pink granite. It's really attractive.
And what depth, Don?
7,600 some feet.
Isn't there a deeper one?
I thought Snort 2 was
Yeah.
pretty deep, but it's not very much.
Yeah.
7,600. Yes, sir. Snort 1, Snort 2 is over 10,000.
Yes.
Okay, well, we can debate this later.
They were done by an oil company, so they're pretty good information.
Yeah, no, I don't doubt that. I'm not doubting anything. So I'll keep on going then. Whoop, pointing the wrong way. Back to the SkyTem. So this is a SkyTem output, and you've got a couple of logs in here to help for control. And here's our initial cut on the hydrogeologic zones. So we've got this shallow alluvial material, recent primarily, up in the top, maybe 100 or so meters thick. Then we've got a clay, this kind of greener stuff, some clay sand coming through here, sandy clay and sand. And so this HGZ2 we're considering largely to be Pleistocene and maybe some of the other White Hill stuff, and then below that this older stuff. So here we have a diagram with the gamma, again, showing where there's more clay, and a couple of other logs portrayed, again, trying to show that we're trying to use all the available data in our interpretation of the SkyTem work. And again, it's following that color scheme of unsaturated, coarser grained materials up towards the top, and then you're getting into clays, clay dominated, mixed with sands and sand stringers and that sort of thing as you go down. Now, here are a series of diagrams that are in the appendix of the report that I wanted to run through, and why I suggested you might want to sit down close. Each one of these will have a location figure, and it shows the SkyTem lines, and then the dark blue lines will indicate what sections we're seeing, where they are located. And we're going to try to do this very systematically, going here, then down here, then I think here, then over here. So that's kind of the progression we're going to do. So here we go with the TDS, where there's TDS, that's these circles. The blue is 150 to 200, 250 to 500. Those are the blues. Green's 500 to 1,000. Yellow's 1,000 to 3,000. And red is over 3,000. I'm not sure you'll be able to see the lines of the different HGZs, but these are the colors indicated for the different hydrogeologic zones we've mapped. Basically, actually, it's mostly Paul who spent hours doing this stuff. And then Max and I have kind of looked at what he's done. And then, again, we have the SkyTem interpretation. The granite, sand, gravel, unsaturated here, clays over here, saline here. And so with that, I'm going to get the rest of the diagrams here. So you can see as we move down here, one thing to note is the basin bottom deepens. We've got it, we think we've got it mapped here, but then as you go further down, and again, so I'm going to go, this is going from here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's a succession, so you're moving downward. So we've got this unsaturated zone, and some clays, but you can see quite a bit of yellow in there, indicating a lot of sands. So, and that's what you would kind of expect. The Owens River came through there, so you'd expect to see some sands and channels, especially in the deeper sediments. You can see the water quality is not too bad either. Got a couple of green dots and then the yellow, so it's not too high. And again, you can see these yellows and green sands, or yellow sands. And then the other thing to note is coming off the Sierra Nevada is you see these a lot thicker deposit of very coarse-grained materials, which again in the different conceptual models you'd expect having much more coarse materials, and perhaps at depth. And as you move down here, you also, there's these kind of rounder features may indicate channel deposits, so channels of sands. That's kind of the interpretation. And then as you get all the way down over here, then you're starting to see more clay, more of a clay deposit, and then some salinity over here. So that's all up in this area here. Next sequence. So then it's just the two lines you see off to the right there. Now we're basically going directly west to east, and a succession going this way. And here, and we've got another diagram that's a little different, a vertical exaggeration I'll show you, but this actually looks like a channel. There's a concentration of sand and gravel there. And you can also see another little feature here. We think this actually is some sort of a little graben with a little lake fault bounding it on one side. And then again, you can see the water quality is pretty good. You've got some clay down here on this diagram. And then you see over here perhaps another potential channel in the area. And this is also a sand deposit here surrounded by some clays. So those are the kind of features we're starting to see in the SkyTem interpretation. That's really what's nice about this tool is you've got, with boreholes as a geologist, you get boreholes and you get this big blank space in between. This helps connect the dots. You have to be careful about your interpretation and what you believe versus what you theorize. But you know, it does provide a lot of evidence that suggests there's a lot of heterogeneity there. Yeah, Tim?
Does that suggest that there is some water coming from the north?
Well, we know there's water coming in from Rose Valley. We just don't know how much. And we don't know whether that's changed over time as well, depending on what the hydraulic head was from each point. Yes?
Sorry, keep bothering you. On your core samples that we have, how do those correlate to the data?
I think it's pretty reasonable. Paul, you want to comment on that? Did you hear the question?
No, I didn't. Can you repeat the question?
Yeah, here, I'll repeat the question. So how do the core samples correlate with the SkyTem data? And it's asking, I guess we're asking for some sort of is it good? Is it poor? Is it reasonable? So maybe you can comment on that in a few words.
I'm sorry. Can you repeat it again? You just fell out just for like.
Okay, how did in your when you did the SkyTem interpretation and looked and developed the conceptual framework, how do you feel that the core samples correlated with SkyTem data?
When we had the core data, I thought it correlated fairly well. But the thing you have to keep in mind is that the resolution on the SkyTem data is often a lot less than what you have in the core data. So when you can see the wells that have, if you step back and saw the kind of average of these layers, I think it fit the SkyTem very nicely. but when you're looking at layers maybe 10 feet thick, you're not able to see that in the SkyTem. That's why we couldn't really use the SkyTem data to map out the sand stringers that you might see in the middle or middle zone HGZ2. I don't know if that answers the question, Tim.
Yes, thanks. Perfect.
So, Tim, from a layman's point of view, 5 to 10 foot intervals on your core samples would be very beneficial to the SkyTem. So why are we not using a lot of this data that we have to compare them?
Well, I think, that we don't have that data in our hands, so we tried to, get all the data we could. We reached out, and, the nice thing about what we've developed is it can be modified. It's in an electronic context. You can bring more data in, and it's all a matter of resources. we want to kind of wrap this up, but again, it can be added to with more detail where there's more detail available. I'm being very careful about making any promises to do more work. So, but I think, your point's very well taken. Yes, Judy? We have a line that goes. Which one? This one? So it's these two lines, this one and that one.
Where are those?
It's right up here. 395 goes right up here, so it's up the hill. Yeah, I mean, BR10?
Is that north of Brown Road?
Yes, I don't think Brown Road goes. 9 Mile Canyon, is that here?
No, further up. That one right there. Yeah.
So it's coming off of 9 Mile Canyon. So I guess we need to put more geographic locations in our insets. Yeah. Okay, let's keep going because I got quite a few slides going and we want to get out of here for lunch, I would guess. Okay, so now we're getting into more interesting area, and so here are the lines again, and they go going down 1, 2, 3, 4, 5, 6. And what I think we want to see here are a couple of features. One on the left, where it's close to the mountains, the Sierra Nevada, you see again these very coarse-grained sediments going rather deep. And then the other thing is this blue feature. And those are the lake bed deposits, the lacustrine deposits, where they're bluish and green, and then when they get dark blue, they're saline. So you can see as you move down that you've got this relatively thick saline lacustrine deposit until you get down to about here on the basin, and then it kind of phases out. There isn't as much saline, and it gets sandier. And that's kind of as you'll see in our hydrogeologic conceptual model, that's really important in terms of the distribution of materials in the basin. That most of the lacustrine, the clays, are more limited by where the river came through and the alluvial deposits came through. And so we've got a lot more coarse-grained sediments down in the south end of the China Lake area. The other thing that's really interesting here is that you see how it's undulating. That, we believe, is related to faults coming through here. And I'll show you a couple of detailed examples towards the end of these diagrams that focus on that, because that's important to understand in terms of flow and character and how these sediments were deposited. Oh, here?
And you should also have BR6. I don't know whether that's on the next one up. I don't see it.
No, I'm not sure, and that's one thing we're working on is getting those labeled.
Yeah, but you surely use BR6 and BR10 for control.
Yes.
And I don't see them on the stone. Yeah, I didn't see it there.
Yeah, you hearing that, Paul?
No, can you repeat that?
Yeah, just there's a note that the way I'd put it is there's some important logs, higher quality logs that should be shown on the diagrams and should be labeled. And so I think we just need to make sure that we've got those labeled. I think we've used all the higher quality data. I mean, that's I think part of Don's point. But I think it's really important to label it so that it's visible. And that's the other thing that we haven't done is we could put a table together with the quality rating that we did, which I think would be useful as well.
Yeah, absolutely.
Okay, so that's the lacustrine portion, basically. And then these are some north-south sections just to show you what we're seeing north to south so you'll get an idea of the geometry. You're all going to understand the geometry of the sediments after we put you through this. So, I don't know, hopefully that's something you like. Anyway, so this is the top section. This is the second section, and this is the third section down. Just wanted to point that out so you can see be sure to know what we're looking at. And what you'll see in this, and this is north, going to the south, and again you see this sand and clay, then becoming more clay, and then we're getting into saline water as you go south, which is what we expect. And this one, north to south, and again, it shows this saline clay doesn't extend that far south, which is important to know. And then you're getting into more interbedded sands and clays as you move south. And this shows coming off the mountains here, with some of the unsaturated zone sediments in the red. And then finally, this one going from north to south. We are picking up some finer grained sediments here that may even be a little bit saline on the south end of this, and I think we've seen that in some of our water quality samples as well. Now we're going to look at this going across the neck, so to speak, of the El Paso, China Lake area. And this is going from northeast to southwest, and the succession of lines is going from the north all the way down to the south. And here you can see one of the features you see here is this appears to be faulted. And it's maybe hard to pick out from up there, but we've got a couple of other diagrams we'll show you that focus in on this. There appears to be a fault, a splay off of the Sierra Nevada frontal fault that runs across the where the El Paso and China Lake area join. And that feature it can be seen in all of these diagrams, or most all of these diagrams to some degree. And the other thing that's interesting, especially if you look here, it looks like there is some sands that pinch out and are contained by clays. So there's a possibility for people who are looking at recharge of an area that might be a pretty well contained area for recharge in the future, because this appears to be all clay up here. And again, we've got some of the boreholes, some water quality to show, and so on. And here you see this feature again coming off. Then it kind of disappears going down here. But again, it's sands. These yellows indicate a lot of sand in here. And then when you, all the way down here, it looks like you may have a channel coming off of the alluvium down here. So these are the kind of features that we'd be looking for possible areas to look for, where the water may be available. And now we're moving into the El Paso area. And we don't know as much about that. We don't have as many control points. But so the diagrams again are north to south. And now we're going from west to east in terms of the way they're shown. And so you see the bedrock up here, and then you've got these unsaturated zone, and this doesn't look real coarse-grained here. It looks again like you've got sands and some clays distributed throughout the area. In this middle section, it does look like there's potentially some faulted features here, and we've got more clay concentrated in this area. And then finally over here, we've got some water quality distributed there, where it's 500 to 1,000, I believe, and a little less than that. And then, again, you've got a clay back here, but again, you've got the same typical unsaturated zone of coarse-grained materials on the top, underlined by some sands and clays. Yeah.
The westernmost, the top section, I don't see any hint of the anticline that was mapped by the oil seismic work in the 50s. Do you have any comment on that?
No. I'm not sure that we would be able to pick up a feature on a line like that, but I mean, I don't know where that anticline was mapped. Was it in the south end of the El Paso? Well, you might see something like that here. I do see kind of a rounding shape. I don't know. It's kind of using my imagination a little bit, though. Oh, horizontal. Is this meters, Paul? I'm assuming this is meters. Horizontal scale?
Yeah, the horizontal scale is meters in that case, yeah.
Yeah, so it goes from 0 on this one to 18,000. The scale is five times the vertical exaggeration.
Yeah.
2,000. Or it's the way the Europeans put it, it's 2.000, which always is, or sometimes it's a comma. Yeah. Okay.
Yeah. Tim?
Yeah.
May I have I have a question with regard to the anticline.
Yeah.
Which orientation is the anticline in?
Yeah, what's the long axis of the anticline? It's north-south. So that would express itself that way. Do you see that feature, Paul? On the south end?
I need to go. Yeah.
You probably not.
Yeah,
Are you following the slides?
I'm trying. The live feed is about 20 seconds behind. But I'm guessing that is it the hills that are kind of green color on section 3, S to N number 3?
No, yeah. Okay. You catching all that? One thing you do see, though, is...
No,
Go ahead.
No, I'm sorry, Tim. I can't. Unfortunately, I can only hear you through the phone.
Okay, well, let's not dwell on it. I guess the point is going back and looking to see if we can see some of the structures that have been mapped. One thing you can see is that the Golar, well, actually, this basin's been tilted to the north and the west. And if you look here, you can see some features that suggest that sort of tilting. But that's just part of the puzzle. So, moving along. And I think this might be the last of these appendix diagrams. So these are these are the ones that go from south to north across the basin, moving from the north to the south. Does that make sense? As far as they go. And so you can see the Sierra Nevada here on the south end pretty clearly. And you don't see a lot of features here. You don't see the thick blue clays. You see a little bit of this as you move to the south in the basin. And then just a few control points in this area is the other thing to note. It is again, we're seeing this coarser grained, thicker deposit here that is of interest, where it looks like it pinches out as you head towards the China Lake area, and then you can see a bit of a fault here as well in these features. But that goes through the appendix anyway. Yeah, I think so. Okay, and so now, based on all of that, this shows the China Lake area, and this shows the El Paso area, a basic concept for the hydrogeologic zones, and you can see we've got HGZ4, HGZ3, HGZ2, and HGZ1. And these are more consolidated materials, less consolidated. This is the clay of the Pleistocene largely, and then this undifferentiated fresher alluvial materials on top. So that's basically, and here's snort 2 that shows it's going down to granite in the Sierra Nevada fault. Then over here in the El Paso area, we just don't know as much, so we've just kind of broken it up into 2 units for now until there's more information available and whether or not there's more of a focus over there. I mean, right now I think we're all interested in becoming sustainable over in this area and, learning more about that area, but I think for now that's where we've ended up with. And this is a series of slides that show the thickness and distribution of these units that we just went over. So HGZ1, and I guess I should go over the colors. So where it's white, it's not present. And just want to differentiate that we've treated these two areas of the basin differently. So we're talking about the China Lake area, not the El Paso area right now. So if it's no color, it's not present. 1 to 100 feet, it's yellow. 100 to 200, it's green. 200 to 300, it's a light blue. And over 300 feet thick, it's dark blue. And so you can see the distribution of this HGZ1 is thicker over kind of where you would expect it, where most of the materials are coming off of these highlands. And then this lake bed deposit, this HGZ2, is much thicker here, and you can see it's not present in this area. And so the lake didn't either extend that far, or else I think more likely it's just been eroded by other materials, replaced by other materials, sands and gravels, and that's kind of where, if you notice, a lot of the wells are in that area because they produce water better in the coarser grain materials. And then HGZ3, it shows that it's 400 to 800 feet thick there, and then over 800 feet thick in that area. And then finally, going to El Paso area, we've got this first unit, and I think we kind of pointed that out, that there were a couple of coarse-grained bodies that are thicker in the diagrams you could see looking at the cross sections, and that's where these are basically. Now this is a kind of a hydrogeologic features map I want to discuss for just a few moments, and then we've got some focus sections to zoom in on some of the features we mentioned earlier. And so the coarse-grained fan deposits that have been mapped are shown here with the cross hatching, the diagonal hatching. Then we call this a hydrogeologic contact, where it's cross-hatched. And what that means is HGZ1 is in connection with HGZ3. There's no HGZ2 there, and 2 is that clay. Clay tends to impede the flow of groundwater downward. And then this dotted material is where we think there's a buried channel deposit. So we've got one of those coming off of here. And then buried deltaic deposits are where there's a line going that way, and so we think we see delta deposit up here. There may be others, but those are what we've got so far. And now for some sections. Again, this shows the location of the sections we're going to see, these red lines, and then we'll zoom in on some of the features. And so you saw this earlier, it was a different vertical scale. Now it's a 10 instead of 5. And you saw the same line basically. But here, again, I mentioned this earlier, this is like a graben and it's the Little Lake Fault zone, where you've got an area that's dropped down relative to the remaining area. And it's sand, a lot more sand concentrated in it. You can see as you move out, it gets more clay and over here. But so that's a very interesting feature there that may be worth looking at more in the future. Sierra Nevada frontal fault, and then here we have this hydrogeologic contact where we see this is the HGZ1 and HGZ3, and here's your clay. So it's there's not much clay there. And moving down further, we think we see the same channel extending down further from that, and that's why we've mapped a channel here where you see this sand and again the hydrogeologic contact where you've got HGZ1 in contact with HGZ3. Then you get this saline clay, and again here's the sand and the faulting. And now moving across the basin, you've got another area. This is a larger area. Again, here's your line. This is a larger area where you've got HGZ1 in contact with HGZ3, which tends to be more coarse-grained. And then your clay is way over here. So that's another important note. And here this has some of the, it's got one borehole labeled, but one of the problems we're having with the labeling of the boreholes, by the way, is we've only got a couple of handfuls that have local names, that are short. So we'll have to figure that one out. But and here we've got another section now that goes from the north up by where Rose Valley, the Neck Rose Valley, then makes a right turn to again show some of the wells, and here they are labeled. We've got BR10, BR6, NR2, and MW32, and it shows how the some of the logs compare with the materials. And you can see, just now I'm going to go this way back, so you can see that this is largely sandy materials mapped in these boreholes that go from HGZ1 to HGZ3, and there's no real big clay bed there. And as you move over, you can see there are a lot more brown ones indicating the clay. And then you've got another little break here, and then out to BR10 where you've got the clay pretty well represented. And then this shows the same section with the SkyTem data. This is the interpretation. Here's the SkyTem data. So we've just removed the color of those HGZ units, and the lines are still there. But now it shows the SkyTem data displayed on it. So again, the yellows tend to be more sands. As you get into the greens and blues, they're more clays. And so you can see how this has gotten mapped then with the HGZ2 going through here and over there where there's no SkyTem data. And then up here where you've got the HGZ1 and the HGZ3 in the basement. So hopefully this helps explain how we got to where we are in terms of the data and interpretation. And now here is one line that's just coming off of the Sierra Nevada, this extension of the Sierra Nevada frontal fault, or another fault, or a series of faults actually that come through here. And so here's your cross-section line going from the southwest to the northeast. I'm standing on the northeast end. And what we see is, again, you can see the color change as you go across here. From this light green to more coarse grain materials at the top. And you can see this kind of coming down here. And that's how this is interpreted to be a double fault here, or two faults coming through here, where you've got this different material change over the space of a very short distance. And so here you've got this clay and sand and the unsaturated zone up here. And so there's some more detail that you can see as you go through here. And this is this is well 33, the district well 33, and well 1 that we've shown here. nice detail on this log. Well, that's called a depth of investigation, and you'll note that that wasn't present on most of the appendix figures I showed, because basically we cut off the interpretation below that. So, I don't know, Paul, are you still there? Because maybe you could talk a little bit about depth of investigation.
Yeah, I can mention it a little bit. What the depth of investigation is, it really depends on the total resistivity that you have in your column, the geological column. And it's basically the depth to which you can directly correlate the resistivities with, for example, lithology or salinity. When you get below what we call the depth of investigation, you still get a signal, but the signal is less reliable. The inversion model isn't able to delineate as well. Below the depth of investigation, you can still see some trends, but you can't directly translate it to what you can above. That's why often you'll clip out the resistivity at the depth of investigation. However, sometimes you can still see signals or trends below the depth of investigation. But anytime you do any interpretation below those black dots that you see on the cross-section, you need to be very, very careful, because it could be a false signal.
So in other words, you can use the information below the depth of investigation as some kind of an indicator, but not necessarily use it for an interpretation.
Correct. And anytime you get below the depth of investigation, it really, really helps to have that you can look at it through, for example, lithology, core samples, lithology logs, or other e-logs. And if you can see the same trends, then you might be able to take more out of the SkyTem data. However, if there's no data to compare it with, then you got to be really careful.
Okay, thanks. Answer your question? Yep, okay. Okay, and here's one more line, and I think this might be the last cross-section line. Again, showing the normal fault along the northern the Sierra Nevada frontal zone, and just there was apparently along this line. This just shows lines that were flown basically northeast, southwest. The distribution of those lines. And so we're seeing some clay and sandy clay in this area. And here's your depth of investigation again. Again, we don't have a lot of data out there. Oh, one more. Okay, so here's that feature I mentioned earlier. So you've got this coarse grain deposit, which came off of this wash. I think this is Freeman Wash. And so you can see this nice deposit of sands and perhaps even some gravels, the unsaturated zone. And then you can see it's more clay below it, and it looks like it kind of pinches off here. So it's a nice little lenticular body of material there, and that's sitting right back in here. And here you've got these two faults, again, that are interpreted based on the SkyTem and other data. And this just shows a compilation of the lines. Hey, Paul, what is this a particular depth? This it's got all the lines in the El Paso area.
Yes, it is. I believe it's at 570 meters elevation.
Okay.
So what this is showing is kind of a cut through the earth of the resistivity.
Right.
And if you see where you have the cross hatching, or not the cross hatching, but the
diagonal line.
That's correct. That's where you can see the resistivity becomes higher, and just to the west of the hatched lines, you can see in the resistivity that you have a lot of the yellow colors, which is the saturated zone, but sand and clays. And what I expect is happening is that you have the fan, you have water, groundwater coming through the fan and flowing towards this barrier, and once it hits this barrier, instead, the groundwater will flow almost directly towards the north, and then eventually come out into the China Lake area across the two faults. And you can really see this happening in the SkyTem data. We were able to use the SkyTem data and map out what we believe is the water table when the lines were flown, the boundary between the saturated and unsaturated zone. And when you look at this, you get a sense that the flow comes basically across the fan, starts out west to east, and approaches this barrier, and then flows north, and then out into the basin.
Thanks, Paul. Okay, and then we just have a few diagrams of water quality distribution left here. And so I'm going to give you an explanation. So we have the TDS. Dark blue is 150 to 250. The light blue is 250 to 500. Light green is 500 to 1,000. Yellow is 1,000 to 3,000. And red's over 3,000. And so this is within HGZ1. And it also shows some approximate contours of TDS by color. So the blue is 500, the green's 1,000. Again, the yellow is 3,000, and pink is over 10,000. So that's what we're seeing based on the data we have in HGZ1. Again, that's the shallow zone. And we're using the same data that DRI and the Groundwater Authority are for this exercise. We actually provided them with a bunch of data. They went through it, they added some data, and then they gave it back to us. And so here's HGZ2. Again, you've got the same color scheme, with the blues representing less than 500, green representing 500 to 1,000, and yellow and red is over 1,000. So you can see the distribution again. So if you notice, there's this kind of sweet spot over in this area of the basin, and that's again where most of the wells are. I think that's kind of the big picture look at that. And it kind of follows the same shape of the where the two zones are interconnected. And here's HGZ3 and 4, and we don't have as many samples there, as is typical with anything with groundwater. The deeper you go, the less data you have. So again, the reds and the blues, and again you can kind of see that same sort of pattern where the fresh water is kind of in the south end of the south and west end of the China Lake area. This is basically, I'm going to spend a couple of minutes explaining this, because it's basically what we call our uncertainties map, HCM uncertainties. So the squares are colored by the number of wells in their square miles. So it's 1 to 5 for yellow, 6 to 10 is green, and over 10 is blue per square mile in the conceptual model data that we have. And then if it's clear, if it doesn't have any kind of lines in it, it means it's less than 350 feet. If it's got diagonal lines going that way, it's 350 to 1,000 feet. And if it's the other way, it's wells over 1,000 feet. And what you can do by looking at this is kind of get a good idea. And by the way, where there's no squares, there's no well, right? So in our model. So you can kind of get this distribution of wells is pretty well concentrated here. But there's a lot of shallow wells here where you don't see the cross-hatching of any sort. It's basically less than 300 feet deep. And then when you've got both, and you've got a combination of both. But basically, you can see we don't have real good coverage in parts of the basin, especially this El Paso area, and then deeper zones out here. And then there's basically along the Sierra Nevada fault zone is another area that there's not a lot of good data. And, that's theory is that, groundwater comes into the basin a variety of ways, but what we haven't really got a real good handle on is how much is coming in from the Sierra Nevada, how much is coming in as mountain block recharge. And there could be a fair amount of that, especially with this Sierra Nevada frontal fault where you've got quite a bit of material there that's got big cracks and there's springs up there. So it'd be good to get a better handle on that. Also, we know that the Owens River probably, because of the way the structure was developing with this, basically this half-graben tilting to the west, the Sierra Nevada going up, we know that this was probably the lower area, so it would be only natural for the Owens River to be kind of flowing on this side and wrapping around. And that's where you see the coarses distribution of sediments. So it would be good to better understand how things are moving in and how much is coming in from this area. We know there's another pretty good-sized sub-watershed up here, and Fremont, it comes in through Fremont Wash. So that's another area that could be useful to understand. And then El Paso is pretty sparse. Yeah. Yeah. Paul? These are square miles, right?
Yeah.
Okay, thank you.
Correct.
Yeah. Are those sections from the TRS? Probably.
No,
Or you just made up your own?
I just made up the square mile.
Okay.
I tried to locate them on the sections, but I'm not sure I hit them exactly.
Well, yeah, and we really, that's another issue is actually we'll go over in data gaps. And I think I'm just got a couple of slides left to go over kind of summaries, but that's one of the issues we've had. Is we've got a lot of information that's not very well located because a lot of our information is coming from logs that had paper maps and that kind of thing that, didn't get, whoops, uh-oh. Okay, good. This should be painted red. So some of the data gaps I've already mentioned, but I think is worth covering. Again, it's the El Paso area, the spatial coverage, and wells and e-logs to consolidated sediments and bedrock. And then this China Lake area, the spatial coverage to the northeast and along the Sierra Nevada mountain front. And then in particular, the whole basin, when you do a groundwater flow model, you want to know about the aquifer characteristics. And the way you get that data is either you use literature-based, which is not going to be very, it's your best guess. Or you pump a well and you have monitoring wells to monitor how the water draws down. And then you measure the water levels and the pumpage and all that good stuff, and you can then measure the aquifer parameters. And so we don't have much of that in this basin. So we really need to work on getting better aquifer parameters to improve our modeling spatially. And then some of the additional data needs, I think just mentioned that from existing wells to collect that kind of information. And then there's also, this idea of better understanding what's going along the frontal fault zone and fracture flow and mountain block recharge along that area to better understand it. And then continuing collection and updating the well construction information so we can better locate the data we have in space. That's just been a real challenge. And then deeper wells in the El Paso area, again along the frontal fault and pilot areas for a brackish study to better understand that. We're working with DRI on doing some modeling, but this brackish study would propose to take some brackish water and treat it. It wouldn't reduce the demand in the basin, but it could reduce the spatial demand. So if by pumping in different areas, you could relieve the stress in areas where there's fresh water. That's one of the ideas behind that. And then identify more wells in the northern part of the basin for TDS, and identify any additional wells in the El Paso area with TDS. And I'm down to the summary. So basically, this has been a good exercise in data collection and simulation and aggregating data into a digital format, which can be updated over time. And the basement's been mapped in the 3D model and 4 hydrogeologic zones identified. New knowledge from the SkyTem data, we've been able to map a number of features and could pull some more with some additional data, and also the approximate distribution of brackish water. And this information will all be freely shared with the Groundwater Authority and the Navy Development Research Institute. And again, it's meant to complement the existing body of data and work, and it's a living model that's readily updatable. So if somebody decides to pull out all those core samples and log them into a digital format, we can pull those right into the data. By the way, I had a project called Stringfellow. This was the first permitted hazardous waste disposal site in California. And one of the first things I did was they cored a lot of the rocks there because it's basically a hard rock basin that had been a quarry. Stringfellow was the name of the contractor who owned it. And so the first thing I did was I took photographs of all the logs. And then I characterized them, I logged them into format. So that's something that would be useful, is to actually have pictures as well as written description. And then you have it saved forever. So just my thoughts. Anyway, I think that's all I have. And, next steps. That's always good. So in terms of the TAC, Well, we haven't set a date for when comments. We would hope to have comments, but I think we'll hopefully take it up at the next TAC meeting, and it may wander into another TAC meeting beyond that, depending on what the response is. But the Technical Advisory Committee for the Groundwater Authority has a copy of the draft report, and we look forward to their input. And then, again, this HCM and GeoGIS database will be made available to the authority. And then just a reminder that we're not done with this. We've got a geostatistical exercise to go through that Stanford will be leading in the probably towards the middle of next year is when I would expect that to be done. Could be sooner, but you never know. We're dealing with Stanford, so. Anyway, any further questions or comments?
The resolution on the SkyTem data, what was the state of resolution?
Hey, Paul, resolution for SkyTem, I know it's feature dependent. It's also lithology dependent.
Yeah. The resolution also depends on how deep you go and how well you're able to invert the data. The resolution will be higher the more the closer you get to the surface, and the deeper you go, it becomes less and less.
Right, and then in terms of lithology.
Yeah, I mean you're getting resolutions of 5, 10 meters, 20, 30 feet. Getting anything thinner than that, you're not able to really.
Okay. Anything else? It's almost lunchtime. Yeah. Yeah, I'm sure we can make that available. Well, I guess with that, I want to thank you for your attention, and I guess I'll call this to close.